Hello all, welcome to our channel Digital Classes by Sai. Have you ever wondered how the modern computers we are using these days are created with that much of complexity? And have you ever thought of learning the building blocks behind these powerful machines? If you did, then this video is for you. I am Sai Avaru and I am a hardware design engineer in VLSI. And I am very happy to share my knowledge with you on various topics of VLSI. As part of it, I welcome you to the video series on digital electronics. If you are a student of electronics or a professional in electronics domain or even a layman who wants to understand about the computers from scratch, this series of video helps you to a very great extent. Let's look at the topics that we are going to cover as part of this video series. The first one is number systems, which is very important for learning about the digital systems. We will discuss about the decimal number system, binary number system, hexadecimal number system and octal number system in this section. And then we'll see about the number system conversions. We'll see how we convert the data from one number system to the other number systems. For example, from decimal to binary. And in the next section, we'll see different types of binary codes. We have so many types of binary codes like 8421 and XS3 and gray code like that. So next we'll see about the logic gates, which are the building blocks for any kind of digital system. And we'll see some of the problems on the logic gates. And we'll look at the Boolean algebra in the next section. And we see some of the applications of the Boolean laws. And we'll see how we can minimize the Boolean functions using the K-maps. And then we'll discuss about the combinational circuits. And we'll look at designing a single bit half adder, and we'll look at designing a single bit full adder and then multiple bit adders. And after that we'll see how we can design the comparators and then mux and demux and then encoder and decoder and then latches. Till this point all these designs are part of the combinational logic. Then we'll see what is the role of the clock signal in sequential circuits. Then we'll see what is a sequential circuit, and we'll see how we design counters, and then we'll see how we can design the registers, and we'll see introduction to some FSMs, which are finite state machines, and we'll see difference between Mealy and Moore state machine, and finally we'll see how all these elements contribute towards the computer design. So we'll start our video series with number systems from our next video. For now, let's discuss about an interesting and good to know topic before starting with the actual subject. Do you know that this piece of analog circuit element, which is called as a transistor, is the building block of the computer? Yes, the processors that we are using in our computing systems are built with billions of these transistors connected together. Let's see how is it so in the next topic, that is computer layers of abstraction. Before going deep into that, let's first get our understanding clear on abstraction. So what is abstraction? Abstraction is hiding the details of an object which are not relevant to the user and showing the details which are only relevant. If we take a bike an example, being the rider of this bike, we need not know the details like how this bike is constructed, how does the engine work, and what is the transmission system used in that bike. We just need to know how to start it and how to ride it and how to stop it. All the other unnecessary details are not required for us. But those other details are required for the bike mechanics. So we as the users are on the higher abstraction level where only some of the details are exposed. And the mechanics are on one abstraction level before where more of the details are exposed to them. Then comes the bike manufacturers where more and more details of the bikes are revealed. So why are we abstracting these details? Because it makes our lives easier. Lesser the details, lesser the problems. This way we can actually draw a clear boundary on who works where. Let's now look at the computer abstraction layers with this understanding. So we all know that we use the computers in our daily life for various applications like internet browsing, programming, and to watch movies and to design graphics and so on. All these applications comes under application layer of the abstraction layers, which is sitting on top of all the layers. This is part of the software side. So the software architects actually work on this layer. They identify these use case scenarios and understand them thoroughly. And they pass on their understanding to the next layer. In the next layer, algorithm developers develop the algorithms. These algorithms convert the use case understanding to the logical flow of information. An algorithm is actually a group of tasks arranged in a logical and sequential order to solve problems. These algorithms are passed on to the software programmers as the requirements and specifications. If you have ever learned any programming language before, you would know about the basics of the algorithms. And it's completely fine if you are not aware of it also. This is the second layer of abstraction below application layer. The next layer is programming language. In this layer, the software programmers develop the code in any of the high-level programming language like C, Java, Python, etc. with the specifications they got from the above layer. Sometimes we can ignore this layer and directly write our code in the next abstraction layer for the advantages with programming in assembly language. But it's not always possible to code in assembly language due to heavy size software codes. The next layer is assembly language. The code that is developed in the above layer in high-level programming language is compiled using the compilers to generate the assembly language code. And programmers make necessary modifications that compiler couldn't optimize, like using the process-specific instructions. Because the compilers could not optimize the code 100% for all the processes. And the next abstraction layer is machine code, where our assembly language is converted into binary, which is zeros and ones. This is the only language that can be understood by computer hardware. Till this abstraction level, we are on the software side. From next layer onwards, we will dive into the hardware side of the abstraction layers. So in the next layer of abstraction, we have ISA, which is instruction set architecture. ISA acts as interface between the software and hardware side. ISA is the one that decides how hardware will decode and execute the machine code coming from the software side. These ISAs are different for different types of processors. For example, ARM processor has their own ISAs and Intel processor has their own ISAs. And next layer is microarchitectural layer. Till now, we have the software flow from application to the lower level binary code that can be understood by the hardware. The microarchitecture layer is the one that implements the hardware that actually executes the code. For example, we need a digital circuit for multiplication. And it takes two inputs and gives one output. And this microarchitecture stage decides how the multiplication circuitry should be implemented. It could be implemented by using adders, decoders, or anything. In the next layer, we have logic gate or registers. Any digital circuit that does any function is formed by using logic gates only. And memories are formed using registers. Even the registers are also derived from logic gates only. Ultimately, everything is designed using logic gates only. We are going to learn how these digital circuits are developed by using logic gates in the entire video series. In the next abstraction layer, we have transistors. So the logic gates that we have talked about in this upper layer are actually constructed using these transistors. If you are a student of electronics, you would have already studied about the analog circuits where the details on different types of transistors are discussed. For those of you who are not aware of how the gates are formed using transistors, look at this implementation of AND gate using PNP transistors. Here, the inputs A and B are given in the base side of the transistors and emitter is connected to the voltage source and the output Q is collected at the collector. And the final and the lower abstraction layer in this computer abstraction layer is physics. This layer talks about how the transistors are built using the physics concepts. In the above layer, we built the logic gates by using transistors, right? So in this layer, we are building the transistors from the semiconductors like silicon, germanium using the physics concepts. So we started with the applications in the top abstraction layer and kept on coming down to the lower levels of abstractions of computers, that is semiconductors. We also discussed how one abstraction layer is built using the below abstraction layer. For example, transistors are built using the semiconductors. Gates are built using the transistors. and the multipliers in the microarchitecture stage are built using the logic gates. And these microarchitectural elements comply with the instruction set architecture and communicates with the software. So here the software is in the machine code, right? And these microarchitecture elements read the machine code from here and execute it. So how this microarchitectural code is formed? It is formed from the assembly language. How did we get this assembly language? We got it by compiling the programming language from the top layer. And how this programming language has been coded? By using the algorithms designed from the above layer. How the algorithms are designed? Those are designed by understanding the applications of the computer. So this way, if you are going from down to up, it is the increasing order of abstraction. If you are coming from top to bottom, it is increasing order of complexity. So this is a brief understanding of how the computer abstraction layers are designed. So that's all for this video. If you find this information useful, please like and share the video with your friends.